Hello, everyone. This is my first lecture in CTNT 2020 on my course on computations in number theory research. Please feel free to stop me along the way. I hope that these lectures are as interactive as possible. We have so the goal of this course, and there is a lot of information already in the website for the summer school. So if you go to our summer school page, then if you go down to my the description of my course in the ctnt.com, the CTNT summer math.ucon.edu. If you go to mini course B, I have a bunch of links there for you to follow and to explore the things I'm going to be exploring. So if you want to open a browser and do those at the same time, then that's great. So what am I trying to do in this course is to show how people use computations to aid in number theory. In all of mathematics nowadays, computation is just a very useful tool, always to start by working out some examples and explore what patterns you might discover, what conjectures you might come up with, and then find more and more data about these conjectures, just so you can see what might be true. So by the way, so there is basically three things that I'm going to try to use during these lectures. First, databases and other databases that are online on different sites that are available, freely available on the internet, mainly the LMFDB. LMFDB.org is one of the most recent and most comprehensive sites for objects of number theoretic nature, and it has a lot of information there that is very, very useful to number theorists. But there are other ones, other sites that are very useful. So, for example, groupnames.org has a lot of information about groups that are that's very useful to look up, and we'll do that probably in a moment. And then we're going to use two programs that are calculators that help in number theory research. So one of them is SageMath. So let me go to SageMath here. And the other one would be SageMath. And the other one would be Magma, which is here. For Sage, actually, I have it installed in my computer. You can use CodeCalc, or you can use CodeCalc, which is an online calculator. So you can use Sage worksheets there in CodeCalc, which is there's a link right here. You can install it. So I have a local installation, a local version of Sage here, so I can do very complex arithmetic like that in the comfort of my computer, and then I can save these sheets in the computer, which you can also do in CodeCalc if you have an account. All right. So for the usage of these databases and these software, I've created a number, or I'm in the process of creating a number of videos. If I can increase this. So I'm creating videos that are hopefully useful to you, but also to just anyone, about how to just a little virtual tour of these things. So I've already done the LMFDB video and the SageMath video, and I will be posting soon a video also about Magma. But I'm not, hopefully you've seen these videos, but I'm not expecting that you have for the content of these lectures. And we're just going to be exploring those things together. Today, I'm going to concentrate mostly on the LMFDB, but I might have to pop in and use Magma or Sage as we go along. So, so here is, by the way, my, oh, I don't know that I'm sharing this. Can you see a window with Magma? No, right?
No.
Right, okay, so how about now? Can you see Magma?
Very good. Yes.
Yeah, so you see Magma can also add numbers, but not like that. 5 plus 8, 13. Okay, very good. So I'm going to be using both things, and hopefully when I do this, you get back to the browser, correct?
Yes.
People can see the browser now. Very good. All right. So so let's get started. So what are we going to do is explore today a little bit of the LMFDB and try to figure out some things that are of interest to number theorists. So I see this, the database has two roles, which is just we gather data that later I can use, and I can use in my own computations, or I can use as examples or as tools for other things. But also something that mathematicians or number theorists are very interested in are some examples that are very relevant, or examples that are the first examples in the tables. So for example, we can look at number fields, and a number field, let me go to my, I've prepared a few slides just for anyone who might not have seen some of these concepts before. It's too big, too small. All right, let's put it like this. Okay, so a number field is a finite degree field extension of Q. For example, Q adjoint I, that is an extension of degree 2 of the rationals. And if you look, the degree is, you consider Q adjoint I as a vector space over Q, then you see that it is two-dimensional over Q. By the way, you can see my pointer.
Where?
Can you see my mouse on the screen?
You have a cursor? Tell us where it's supposed to be, pointing.
Well, if you don't see it, then no. All right. So a number field such as Q adjoint I, so you see that it's generated by 1 and I. So over Q, so it is two-dimensional as a vector space over Q, and that's the degree of the number field. If you take, for example, Q adjoint the square root, the cube root of 2, then that number field is generated by 1, the cube root of 2, and the cube root of 4. So it is three-dimensional over Q, but there is one issue with that number field, is that this does not include some of the other roots that would be the root, what we call the minimal polynomial of the cube root of 2. So for example, I is a root of an irreducible polynomial over Q, namely x squared plus 1, but minus I, which is the second root of x squared plus 1, is also in Q adjoint I. And I'm not going to define what a Galois extension is, but that is essentially, we say that an extension is Galois if all the possible roots of the polynomials that define the generators of the number field, if all the possible roots are in the field itself. So here I and minus I are both in the extension, and the extension is Galois. But for cube root of 2, we have that the extension is not Galois, because cube root of 2 is a root of x cubed minus 2. The other roots, you need the third root of unity rho, and the other roots of that polynomial would be rho cube root of 2 and rho squared cube root of 2. And since rho cube root of 2 is not in Q adjoint the cube root of 2, the extension is not Galois. Not all the roots of x cubed minus 2 are in the field, and the extension is not Galois. Anyway, that is something that we're actually interested in, is what Galois groups appear over Q for number fields. So, by the way, in the LMFDB, you can look up number fields. So there is, you can look up number fields up to degree 47 with some ranges in discriminant. And one nice feature of the LMFDB is that you can, anything that is underlined like this, that is something that you can click and look at a definition. So like I said, a number field is a finite degree field extension of Q. And we can explore what fields are there. So for example, you can start with degree 2. And here is a table of degree 2 extensions of Q ordered by discriminant. So here is the extension we were talking about. Q adjoin I is this extension, and the discriminant of this extension is -4. The discriminant being some invariant of the ring of integers of the number field, which controls, it gives you some idea, well, first of what primes ramify in general. It gives you some idea of the arithmetic complexity of the number field in some sense. And if you look at number fields by discriminant, then you can see that there is the smallest possible discriminant in absolute value is -3 and is given by this other number field. So the extension of x² minus x plus 1. All right. So we can figure out what that one is. So for example, I can go to Magma and I can define that number field. So let me not mix Magma and Sage code. So I can define polynomial ring and over the rationals, and then I can define the number field that is defined by what was it, x² minus x plus 1, x² minus x plus 1, and then I can look at that number field. And there was an error because I'm mixing some of the notation of Magma and Sage. In Magma, you do colon equals to define things, and then that number field. We can figure out what is the degree of the number field by doing so. Okay, degree of K. All right, well, that's not a good start. All right, anyway, so this is a quadratic number field, and it corresponds to the extension that is adjoining the square root of -3. Okay, so I'm going to be also adding some homework to the course. So if you go to in the summer school page, there is a number of exercises that are appearing already here. I will be updating this page with several problems. So one problem that is of interest is to find, as I said, number fields, for example, with the first example of a number field with a certain characteristic. The first example in the table, so if we're ordering first by degree and then by discriminant, what are examples of each discriminant, for example, and some other feature. For example, in here, I'm asking the first exercise asks to build a number of table just of number fields with the smallest discriminant in each degree. So what we saw is that when I looked at number fields of degree 2, then the one with the smallest discriminant is this number field right here, which you can call it by a root of this polynomial or simply Q adjoin the square root of -3, but you can do that in other degrees. For example, I can look up number fields of degree 3 and then see what is the number field with the smallest discriminant that appears in the tables, which in the LMFDB, the tables are can you hear me? Somebody said that I can.
Yes, yes, yes.
Yeah. Yeah. Did you lose me at any point?
No, I don't
No.
think so.
Okay. Okay. All right, so one of the most important features of an LMFDB is the completeness of the data. So the data in the LMFDB is gathered in a very consistent way and a very accurate way, so that we know about the completeness of the data and the reliability of the data. So if you want to click on that, the completeness of the data explains how complete the table is. So it contains complete list of fields with the absolute discriminant less than given bounds. So for example, for degree 2, all degree 2 fields up to absolute value discriminant 2 times 10 to the 6 are included in the data. So I know that certainly the smallest discriminant is in the data. Okay, and also about the reliability of the data, it gives you some explanation of what is our reliability on the data, and that's that those fields change in every page of the database. It explains how the data was gathered. All right, so by the way, as I explained in the Sage video, once you have a number field in mind, for example, this number field, another great feature of the LMFDB is that you can go down to downloads, and you can download, for example, Magma Code for that number field. So this is a ton of Magma Code that is going to give me a lot of different invariants. I'm going to copy and paste it, and I'm going to put it here. And then I'm going to submit and see what it says. Okay, so it returns all this information that is asking about the number field. Oh, that's what happened before. I didn't put the semicolon. Yeah, anyway, but anyway, you can define the number field, you can give you the degree of the number field, the signature, the discriminant, prime divisors of the discriminant, and integral basis, the unit group, fundamental units of the unit group, and it's all returned by Magma in this window down here. Okay, so that's a nice way. If you don't know how to do something in Sage or Magma, you can grab it from the LMFDB, and that's some feature that I use often. By the way, also something that is very useful is that if I do this and I copy and paste that, it doesn't, typically this is some image that you can't paste anywhere, but in here, actually, if I copy that, it's copied somewhere else as something that I can paste in probably like LaTeX code or even in Magma. So let me see what happens if I try to paste it here. You see, it's actually already sort of like LaTeXed, which is very nice. All right, so so as I said, we are interested in not just a database for the sake of having the whole data, but there are questions that are related to these questions. What is the smallest absolute value of a discriminant for a given field, for a number field of a given degree? What is the smallest value of the discriminant? And then also, which can be rephrased in terms of the root discriminant. So there are conjectures about what that can be and what are those bounds. So that is something interesting. So that's why one of the questions in the homework is start with building a table of number fields of the smallest discriminant for each degree. Those tables are nice to have just because they give you a toolbox of examples that you might later want to try out. And you might want to record a little bit more about the number field. So the number field, you might want to record a minimal polynomial that defines the number field, the discriminant, maybe the Galois group of the number field. The number field itself does not have to be Galois, but it will list the Galois group of the polynomial. So this field is not Galois over Q. So when it says that the Galois group is S3, it means the Galois group of the closure. All right, so what else can we do? So the second problem, maybe this is too small for you to see. So the second problem that I would like you to explore with LMFDB is the inverse Galois problem. So the inverse Galois problem is the following. So as I said, for example, in this example, in Q adjoin I over Q, the Galois group is Z mod 2. It's just a quadratic extension is Galois, and the extension is, the Galois group is just Z mod 2. And we can go to the LMFDB and look at Galois groups, and then look at what Galois groups appear in degree 2. And that's the one Galois group that appears in degree 2 is Z2, which is a cyclic group of order 2. So we can click on it. And I'm waiting for the LMFDB to respond. By the way, again, let me know if you have questions at any point. LMFDB is taking sweet time to get information about ZMod 2. All right. Let's see. There was just something bad with the connection. Let's go back and look at another group. Let's look at degree 3. Let's look at S3. Okay, here is S3. This is the group S3 as a Galois group. So it appears as the Galois group of a cubic polynomial. That's what the degree means here. The Galois group of irreducible polynomials, a transitive subgroup of Sn. And the degree here is the degree of the polynomial. So in here is saying that S3 appears as the degree of the Galois group of a cubic. And we can actually look in the database. We can look at number fields with this Galois group. So if you want to find a Galois group or a number field that has S3, here it is. Well, we already found one before, but here it comes again in this list. If you want to go and find polynomials that have more exotic Galois groups, so let's say, for example, you want an A5 as a Galois group, then here is A5 as a Galois group. This says that A5 appears as the Galois group of a quintic polynomial. And if I go to number fields, then I can find by discriminant number fields that have A5 as a Galois group. So here is the discriminant of such number field. Very many questions can come up right away as you look at the list of such things as, for example, is there a number field or a polynomial of degree 5 such that the discriminant is a power of 1 prime and the Galois group is A5? Well, you can explore the data and see if, oh, there you go, there is such a thing, okay? But then you have to go up to 653 square in discriminant to find one polynomial that has exactly 1 prime as the 1 prime power as its discriminant. All right, so we can go back again to Galois groups and keep exploring the inverse Galois problem. We can look at other things like PSL 213. We can see this is the group 14T30. It appears in degree 14, such a group, and then you can find out what number field has such a Galois group. For example, in the tables, this number field has such a Galois group. All right. And somebody said in the comments that maybe there are too many fields with Galois group C2, and for sure there is a lot in the database. But I think I was trying to go to the website for C2, and that should have bring me to just the page for the group. Oh, now it worked. Okay, here is a group, and then if we click on number fields of degree number fields that have C2, Z mod 2, here's a list, and here's the smallest one of such ones. All right, so the problem in the homework Where is the homework? Here's the homework. The problem in the homework is for you to explore the inverse Galois problem. So we start maybe first of all, do you have in mind a table of finite groups or a place where to find such groups? I have a place in mind. As I said, groupnames.org is actually a very useful site that lists groups by order. So at first, the page is a little bit intimidating here, but you can see here groups of order 1, groups of order 2, and that's how they're organized. So I have, like, right here at my fingertips, I have a complete list of groups, for example, up to order 10, or you can go farther if you want. It just, you know, there's a lot of groups. There's a lot of finite groups up to isomorphism. So you can find all these, and then, for example, the quaternion group. Does the quaternion group happen as a Galois group? Well, we can try to figure that out. Okay, so you can try to go in the LMFDB, find the Galois group that corresponds to the quaternions, and see if that is a Galois group of some number field. Okay, are there any questions so far? Let me see if I have that in these here. Any questions at the moment?
Do you want a question?
No, not necessarily. If any of the attendees have questions, do you have a question, Keith?
No.
Okay. All right. So, well, anyway, let me know if a question comes up. What else can we explore in the database? I'm a big fan, if you don't know, about elliptic curves. My T-shirt is about elliptic curves right now. So let's try to explore elliptic curves. So what are elliptic curves? We can expand the definition here. We can go to my second slide here. Right. So what's an elliptic curve? An elliptic curve is a smooth projective curve of genus 1 with a point defined over the base field. Okay, so if the elliptic curve is going to be defined over the field K, we need at least one point O defined over K. And there is some proposition, some algebraic geometry tells you that you can actually give what we call a Weierstrass equation for an elliptic curve. So they are always, any elliptic curve will have an isomorphism to, there will be some coefficients in K and an isomorphism to an equation of the form y squared plus a1xy plus a3y equals x cubed plus a2x squared plus a4x plus a6. So for example, let's just look at a few elliptic curves. So if you want to browse elliptic curves in the database, we can look by, well, let's just list some elliptic curves right there. It gives you a list of elliptic curves. The elliptic curves, just like before, number fields were listed by their discriminant. Now we actually list elliptic curves by their conductor. So the conductor is another measure of some sort of like arithmetic complexity of elliptic curves. It also keeps track of some sort of bad primes, primes of bad reduction. So the first elliptic curves in the database are those of conductor 11. And here is 11A3, for example. It's a pretty nice elliptic curve. You can see a graph there. And what can we do with elliptic curves? Let me show you also what one can do with elliptic curves, if I can dig it out here. So I can look information up for, say, in Sage. I can copy all this into Sage myself. Let me see if I can, well, instead of doing all that, let's just define the curve. Okay, in Sage, I can define the curves, shift enter to to define the curve, and then I can go back to, where was it, here, and then I can find, for example, what integral points are there on this elliptic curve, and it will compute the integral points. So there's only 2, 0, 0, and 1, 0 as integral points, and then we can find, for example, what is the torsion of this elliptic curve. Is there any torsion points? Yes, there's a point of order 5. All right, so let's see what is the Mordell-Weil group. So if you have an elliptic curve, you have the Mordell-Weil theorem tells you that what's called the Mordell-Weil group, so the set of all points on E with coefficients in K, that's the set of rational points on E, that is actually can be given the structure of a finitely generated abelian group. And the theorem on the structure of finitely generated abelian groups tells you that then the Mordell-Weil group is isomorphic to a direct sum of the torsion part. So that is the subgroup generated by points of finite order, which is a finite group, and the integers. So some copies of the integers, and the number of copies that are is the rank, we'll call the rank of the elliptic curve. So we can also compute the rank of this elliptic curve over here, and this elliptic curve has rank 0. The torsion is 5, so there is 5 points of 5.5. Let's look at it here. So if we go back, LMFDB tells us this. So there is the structure of the Mordell-Weil group is Z mod 5, and the generator is 0, 0. Right. Okay, and the LMFDB will give us a lot of more information about this elliptic curve. And so something, for example, that is of interest is finding what types of isomorphism types are there for elliptic curves over a number field. For example, over Q, what isomorphism types are there for the Mordell-Weil group? One theorem of Mazur tells us what are the possibilities for the torsion subgroup. So the torsion subgroup is either cyclic, Z mod n, for n equals 1 through 10 or 12. So that means that there is no elliptic curve that has, that the torsion is just, it has 11 points, or that there is a point of order 11. Or the other option is that it's bicyclic, Z mod 2 cross Z mod 2m with m 1, 2, 3, or 4. All right. So one can go into the database and start finding such examples. So let's look in the database for some of these examples. So you might want to see what is the first elliptic curve on the database that has a point of order 12. So let's see. So here is such elliptic curve is 30A6. So by the way, there are other databases that have that predate the LMFDB, and that's one very famous one for elliptic curves, very well known, is the Cremona database. So Cremona had his own system to label elliptic curves, which differs slightly from the one in the LMFDB. The LMFDB is perhaps a little bit more systematic, and so the LMFDB keeps track of both labels because they are all both very common. So here is 30A6, and but you see when I typed the order, it was the order of the group. So this group, this torsion group, has order 12, but there is no point of order 12. So I didn't do my search correctly, but what I was looking for was an elliptic curve with a point of order 12. Okay, so how can I fix that? I can fix that by looking at here. There's a torsion order. Let's see what they mean. They mean the order of the torsion subgroup. So that's not what I want if I want an elliptic curve with a point of order 12. So here, I have all these windows blocking my view. Let me see. I want the torsion structure to be Z mod 12. Search again. Here is an elliptic curve now that the torsion structure is Z mod 12. So here is 90 C7. And this elliptic curve now, the Mordell-Weil group is Z mod 12. It's actually interesting to just find a graph of where that point is and where the multiples of that point are. We'll do that next time in Sage Math, in Sage. So here, I'm going to open this graph here so you can see it a little bigger. So in this graph, we're going to be able to graph not only the elliptic curve, but also the point, and maybe we can play around with those images next time. All right. So here's an elliptic curve with Z mod 12 at this group. And that is the smallest one, the one with the smallest conductor in the tables. All right, very good. So here is a problem that I have for you in the exercises is the following, which is that, okay, so there are, as I said, from Mazur's theorem, there is 15 types of torsion subgroups up to isomorphism. So what I'm asking you is to, well, first build a table of elliptic curves with each of the possible 15 torsion subgroups up to isomorphism and the smallest possible conductor. So you can go to the LMFDB and look at the tables and have a toolbox of elliptic curves with different torsion groups. Very good. But then so elliptic curves also have a discriminant, and the discriminant is a slightly different invariant of an elliptic curve. So for example, this is an elliptic curve with conductor 90, and I can look at the discriminant, and the discriminant is very large in terms of the absolute value of the discriminant, and there is like 3 different primes dividing the discriminant. And one might ask, are there elliptic curves with a structure torsion subgroup Z mod 12, but where the discriminant is 1 prime power, like we did with the with some of the number of fields with a different Galois group? Is there such a thing? Or is there an elliptic curve with that torsion and a smaller discriminant? Is this the smallest discriminant that happens with this torsion subgroup? Well, that's something that one can explore in the database and look at the discriminants of other elliptic curves, and you can figure out how to look through the database and how to do a search, so I actually get perhaps the smallest discriminant of all with that torsion subgroup. All right. Even farther down in that task is finding elliptic curves with each possible torsion subgroup and rank. As I said, we're interested not only in the torsion subgroup, but we're interested in the structure of the entire Mordell-Weil group. So the Mordell-Weil group, there is going to be a torsion part and the rank of the elliptic curve. And then we would like to know what combinations are there for this. Well, the torsion subgroup there are 15 possibilities. And then for each one of those torsion subgroups, what are the possibilities for the rank? That's an open question because we don't know how large the rank can be. The rank, we know that it can be at least 28. Elkes found an elliptic curve over Q with trivial torsion subgroup and the rank being 28. But then there are other elliptic curves with other torsion subgroups, and then we know some. There's a page with these such records of elliptic curves. I thought there was some. Was there? I thought there was a table of elliptic curves by rank. But in any case, I can look at the database and start looking for elliptic curves. Let's try with ZMod 12. And is there an elliptic curve with ZMod 12 and rank 2? No matches. So what happens is that at least in the database, there is no elliptic curve in the database with ZMod 12 as its torsion structure and the rank equals to 2. I'll send you a link to a page that keeps track of what are the known records for elliptic curves with a prescribed torsion structure. And one of the problems I'll add to the sheet is some sort of like challenge for you to find elliptic curves with a given rank and a torsion structure, which would add your name to the list of the records if you found such an elliptic curve. It's very difficult. So there's a lot of elliptic curves in this database, and there is no elliptic curve with ZMod 12 on rank 2. Let's see if there is an elliptic curve with rank 1. Yep, here it is. So this elliptic curve of conductor 4290 has the Mordell-Weil group structure is 1 copy of the integers and ZMod 12. So that's nice. You might also want to ask other things. Another interesting question is, can you find the elliptic curve in the database with the most number of integral points? That's another question that we ask ourselves, is whether we can find elliptic curves with a minimal model and a lot of integral points. How many integral points can you find on one elliptic curve? By the way, look at that graph. The graph of this elliptic curve almost looks like it's singular, but if you were to zoom in that what looks like a node, there is no node there.
Can you zoom in?
Maybe. Let me see if I can zoom in enough. We can do that on when we use Sage. That doesn't help much. No. We can actually zoom in using Sage. Maybe later in after class we can try to do that. All right. What is my last question about this? By the way, the rank, there is some sort of like there's some relationship though. Once you've requested that the torsion subgroup is large, then it's actually hard to find elliptic curves with high rank and that torsion subgroup. But if the torsion subgroup is small enough, then you can find things in the database. Or for example, if I choose instead of ZMod 12, I choose point of order 2, and I try to choose rank 4, see if we can find anything. No matches in the database, but we know those exist and we know examples. But at least of rank 3 and at point of order 2, that's in the database. You can also look in the database, what is the completeness of the data. So these data contains 3 million elliptic curves with conductor at most 500,000. So that's one of the limitations of this database. Okay, so my last question is, and some other question that is very of interest is, are there elliptic curves with a prime conductor or a prime power conductor? And you might want to compile a table of elliptic curves with prime conductor, and maybe that's too small for you to see. So one of the exercises is to start with finding elliptic curves with a prime conductor. So let's see if I can find some elliptic curves with prime conductor in the tables. So if I start looking by conductor, well, yeah, 11 is a prime, so the conductor is 11 for this elliptic curve. So those are elliptic curves with prime conductor. You can go down to, let's see if the conductor 37 has any elliptic curves. So yeah, there's elliptic curves of conductor 37. Are there any elliptic curves of conductor 23? Nope. there are no elliptic curves. That is complete, so we know there are no elliptic curves over Q with conductor 23. However, there are a number of fields, and over a number of fields, that might be a different question. Whether you can look at the conductor norm 23 and whether there are elliptic curves with a conductor 23. And it turns out that yes, the conductor for some elliptic curves over a number field can be 23, or the norm of the conductor can be 23 over some number fields. But the question at hand here is over Q. All right, so those are just some of the questions that one can start looking at using LMFDB just to compile tables of data that are beyond what they have, just sort of examples that are smallest in some form. So given some, if you organize your data in some way, can you find the smallest such example? So one can start looking at elliptic curves up to a certain bound, and then with the smallest discriminant, with the smallest conductor that has some property related to the Mordell-Bay group, for example, and so on. You can also do such searches also about, instead of elliptic curves, about modular forms, like what kind of things appear in the tables of modular forms that are in the database and so on. All right, so next time we'll keep doing some computations. We'll do some practice on how to do things with Sage. And I'll go back to some of the notes from the other instructors, and I will be computing some of the things that they are doing in class using Sage and using Magma, so you learn how to do those things. All right, so I'm going to stop the video here, and thank you for watching.